But before I start, I want to say just a few things about myself and about MaibornWolff. Well, my name's Marc, and I'm a software architect at a company, German company called MaibornWolff. We do custom software development for larger enterprises in the machine construction, automotive sector, transportation, like different types of sectors. And we have about 550 to 600 employees, and about a fourth of them does IoT projects in the IoT sector. And today I'm going to talk about how we built a data analytics platform for a German car manufacturer. And I want to go back to the beginning, how we started. So let's go back to the beginning. Like many others, in the beginning we started running an analytics platform based on Hadoop. So we were running a Spark on Yarn, and we were crunching data stored in HDFS in a batch mode. It's like what pretty much everybody else was doing a couple of years, 5 to 10 years ago. That's also how we started. But the whole experience wasn't a very pleasant one. Everything took a lot of effort. Needed a lot of effort to operate the cluster. Was a lot of effort to automate things. We weren't happy with the whole resilience and of Yarn. We had to restart our Spark jobs manually, and all in all, it didn't really work well for us. And also, we couldn't really run all of our workloads on Hadoop because Yarn didn't support containers, didn't support databases. So we started to look for something else. And we also realized one thing, and that is that actually life doesn't happen in batch mode. And that the world actually turns faster. That's especially true for IoT projects, where you very often have devices in the field and you have to react to things that these devices are doing. Doesn't matter if it's household appliances or cars, it's always very similar. So a common stack for this, or for this type of scenarios, the term fast data has been coined over the last couple of years, has become popular, and the common stack for this is the SMAC stack that I'm going to talk about in a second. So originally, a couple of years ago, we mostly had, we're building KPIs, and doing daily, monthly reporting, using big data clusters for billing and similar things that were reporting basically what happened in the past. But especially with the IoT use cases, it became more and more important to react on what was happening in real time. So today, we're trying to solve problems in real time or near real time, which means, for example, things like dynamic pricing and routing, for example, as our colleagues from Uber are also doing. But you can't wait for a nightly batch run to do so, so you need something like real-time streaming to do so. As I said, a popular solution for this became the SMAC stack. And the question is if the SMAC stack is also useful for the Internet of Things. Before I answer the question, I just want to go quickly through the data processing pipeline, how it looks like with the SMAC stack. So you have here. So you have some kind of devices somewhere on the internet. In our case, it's cars that are producing messages, that are sending messages based on certain events that are happening, or time-based messages. Then you're ingesting the data into Kafka. You analyze them with Spark and store the data, the raw data and the pre-processed data in Apache Cassandra. And then you act or visualize things depending on what you just processed using Akka. The first problem with the SMAC stack is for IoT that actually an MQT broker is missing. So it doesn't really work to connect all your internet devices directly to Kafka for multiple reasons. One problem is that Kafka has not been built for this use case. So it hasn't been built for thousands or even millions of devices having constant connection, keep losing connections. It hasn't been built with a publish-subscribe mechanism in mind that needs hierarchical topics. So you can, let's say, address certain fleet of cars and not just all the cars. And another thing is that in IoT projects, you usually have very constrained devices that are not even powerful enough to, let's say, use HTTPS because they don't have enough processing power. So they really need a protocol like MQTT that doesn't need a lot of resources. And that's why, in my opinion, you really need something like a MQTT broker, and we're using HiveMQ as MQTT broker. And also what can be a problem, I mean, depending on your setup, is that if you're using something like Mesos or Dcos, then usually Kafka is behind some load balancer or reverse proxy, and the Kafka library doesn't support load balancers or reverse proxies. So you have to find certain hacks and workarounds to even get that working. So, and actually, as often the world is more complex than marketing terms like the SMAC stack. So our whole technology stack looks actually a bit more complex, and this is even still a bit of a lie because there are a few more things, but those are the main parts that we're using. So how does our data processing chain look like? So we have the cars that are connected to the HiveMQ MQTT broker. They're transmitting a lot of data. If you want to think about numbers, just think about thousands or millions of devices that are sending, if they're active, like a message per second. So you have really a massive amount of data coming in. Then what we're doing is we're forwarding all the messages that coming on the MQTT cluster directly into Kafka. So we have forwarding services based on Spring Boot and some Python services that also take care of a few things. So we're ingesting them into Kafka, so it's stored as quickly as possible. Then we're using Spark streaming for the data processing, and we also use some Flask-based Python services in our processing chain. Then we store the data in Cassandra, HDFS, and Elasticsearch, depending on what we need the data for. For example, Elasticsearch is really our main database for the end user web front end, because it can do two things well. That's filtering and aggregating. And that's basically what you need if you want to calculate some kind of KPIs during runtime. And that's what Elasticsearch is really good for. So the raw data all ends up in HDFS. And we started introducing Cassandra because we wanted to use it as a replacement for HDFS, because HDFS is not really built for these many small messages, and you have to put a lot of effort into it to, save enough messages so you can create big files, and that's not really the use case what HDFS is made for. But we ran into, and the thing is we don't want to pay licenses to data stacks for the enterprise edition, or basically it's not even an enterprise edition more of Cassandra, it's more like a fork or let's say Cassandra compatible application these days. And the open source Cassandra doesn't support all our requirements towards data protection that we need to fulfill data protection laws in Europe. So we are probably going to replace Cassandra with something else, but we haven't chosen yet. So maybe CockroachDB or something else that helps us to fulfill it. Problem is there are not that many choices of column-based databases to choose from. Then in the Act Visualize step, we have actually 3 types of front ends depending on the user. We have a web front end built on Vue.js. We have for the more, let's say, professional users, we give access to Kibana directly so they can create more complex queries. And for data analysts, we provide Zeppelin instances. Some are also using JupyterLab, but our main tool is really Zeppelin. So each user can choose the front end on his or her requirements. The services that are acting based on data we're processing are either built with Spring Boot or lately with Micronaut.io, because it saves a lot of resources. I don't know if any of you are operating Java-based services, but in the past they used up a lot of resources, especially memory. And with newer JDK versions, it's become better. So like for a Spring Boot service, we're now at 400 to 500 megabyte of memory usage. But with Micronaut.io, we're bringing it down to 150, 200 megabyte. So if you have a lot of service instances, as we do, that adds up to a lot of savings if we use Micronaut.io. We also have a few Python services that use even less, but most developers want to develop in Java, at least in Germany, and know Java the best, so we're going with Spring and Micronaut.io. And actually, that's not everything, because next to the, well, visible world, there's also kind of a hidden world with all the tools that are enabling developers to develop things. So we have GitLab CI, we have Nexus, we have Prometheus and Grafana for logging, monitoring. We have Elk Stack for centralized logging, and so on and so on. So there's a lot of tools that aren't part of the technology stack for the business side, but they are there and they have to be operated and they have to be deployed and have to be taken care of. So with all this complexity, of course, the question is wouldn't it be great if there was a tool that can help me with all that complexity and make it easier to provision and to operate all these technologies and support all of these workloads from container to databases. And as might come as a surprise, there is. It's called Dcos. And that's really why we chose Dcos in the beginning. There were, back then, they're not paying me money, by the way. Back then, there were a lot of discussions if we would go 100% with Kubernetes, plain Kubernetes, or if we could go 100% with Dcos, and because we wanted to offer the developers really Kubernetes, and but it didn't really support all of our workloads, or we would have to put a lot of effort into it. I mean, you can run all these workloads on Kubernetes, but the effort can be very high to get the things up and running, because I know we've done that in other projects, and it's a lot of effort. It can be done, but it's expensive. So we ended up choosing both, actually. So our services are running on Kubernetes, the stateless services, and all other services, stateful services, are running on Dcos, including stateless services that are closer to the data and aren't really providing any business functionality towards the user or towards mobile apps or cars. So next I want to look a bit closer at the architecture we built, and I want to give you a look at 3 of our design decisions, and then I will tell you a bit more about how we set up the cluster itself, how we set up Dcos. So the first thing I want to talk about is about basically the ingest part. As I said before, we have all the cars that are connected to the HiveMQ cluster using MQTT. They're transmitting a lot of data. Of course, there's also services, functional services that send data to the cars, but that's not depicted here because I'm only talking about the analytics part. The data comes in on the HiveMQ, as I said. Then we have those forwarding services that do nothing else but subscribe to HiveMQ topics and forward the messages to Kafka topics. The idea is to persist the data as quickly as possible so no data gets lost. HiveMQ as an MQTT broker is not meant for storing the data for a long time. It's meant for the data to be processed quickly. So we have a lot of forwarding instances, and we have multiple instances per topic. So we make sure that if one fails, the data gets still forwarded to Kafka. Still, if a message is in flight, so it's just in the memory of the service, it's still possible that data can get lost. Luckily, actually today, the company between -Q is announcing an integration with Kafka, so the data gets stored directly into Kafka from -Q, so you can't lose any more data doing what we're doing. Then, when the data is stored in Kafka, we're persisting the raw data in HDFS and Elasticsearch, and still also in Cassandra. And we have, that's the second important thing here on this slide, we have a replay service or replay services that allow us to replay the raw data back into Kafka. If we want to do reprocessing of historic data, imagine that you have a certain KPI and the algorithm for the KPI has changed. So you want to recalculate all the historic data, so the KPI is also correct for older data and uses the same algorithm for older data. So you need a way to be able to replay the data into Kafka and then use the streaming pipeline again with the historic data. Actually, and that's one thing that was missing on the slide before, like where I said I was lying a bit because it wasn't a complete picture. In that case, it's a Python-based service, but for reading the Parquet files, we are using something else again. So there's here and there, we're optimizing it, but in general, the main tools I did show earlier. The second design decision was to build a modular streaming pipeline using Kafka as for handover between the individual streams. So when we stored, after we stored the raw data in Kafka, a first stream depicted here on the left deduplicates events because probably because of bugs, we keep receiving duplicates of events from the vehicles. And the first thing is we want to deduplicate them. Then we store the data again in Kafka. Then another stream is picking up the events from the respective Kafka topic, is cleaning the data, is filtering it, is trying to repair it where possible. Then again stores it in Kafka. Then another stream is picking up the data and is normalizing the data, like using the same, for example, same date format and things like that. So the data has all the same format. And it will also extend the events with master data, for example, or other fleet-related data. Kafka, the stored data gets stored again in Kafka, and we have then again persist services and streams that store the data in Elasticsearch and HDFS. And in the next step, we create business objects. Business objects are things like, in our case, it's like a trip. A trip consists of a lot of events, and many people are interested in the trips and not the individual events. So we create those, again, store them in Kafka, and then as last step in the pipeline, we have, for different KPIs, we do pre-calculation, so they're fast during runtime, and that's the optimize step where we pre-calculate certain attributes on which I can later filter and aggregate in Elasticsearch. That's performance optimization, basically. Along the step, what we're also doing is, in order to always be able to use as much data as possible, is that if a data field is corrupt for some reason, like what happens often is that we have a date of the 1st of January of 1970, then we just put an error marker on that data, so we're able to, that's basically a flag, and later on we can filter out that data if a KPI needs that field. For KPIs that don't need that field, they don't care about that error and still can use the rest of the data contained in the message. And the third design decision is that we wanted to build an architecture for our users. And by users, I mean the end users, the business users, but also the developers. And that's why we decided to provide each type of user with their own front end that is optimized for them. And we also wanted to give the developer the best possible experience. And at least in Germany, pretty much everyone is using Kubernetes these days. So we decided to give the developer Kubernetes as a development platform and runtime environment. Back then, as I said earlier, Kubernetes was not available on Dcos yet. So we set up our Kubernetes clusters with our own automation on AWS. So it's not running on Dcos. But now it could run on Dcos, but since everything is working, everything is automated, it doesn't really make sense for us to change that. But for anyone interested in Kubernetes on Dcos, the next Dcos version, the 1.13, there will be very sweet additions for running Kubernetes. It's going to be very nice. So can look forward to that. Maybe ask the Mesos colleagues about any details they want to give at this point of time. All right. So as I said before, all the functional services are running on Kubernetes. That means front ends and third parties are accessing the data, the services through an API gateway, and we have adapter services that are forwarding data to other third parties like Inrix or similar companies. About Zeppelin, there was one thing missing for us. Back then we decided to use Zeppelin because it supported Spark better than JupyterLab. Back then Jupyter notebooks didn't really support Spark. And but we didn't have anything like Jupyter Hub to instantiate to manage our Zeppelin instances. So we built a tool called Airfield that we also made open source. You can find it on GitHub if you're interested in, which is very nice if you can, in order for a normal person to be able to manage Zeppelin instances without having to go through Dcos. Okay. How did we set up the cluster? We actually built only one cluster for all our environments. That means we have a test, integration, and production environment running on our Dcos cluster. The reason behind this was that we wanted to be able to be as flexible as possible regarding the usage of resources, so we can always use our resources where we need them and don't have to statically give them to a, let's say, test or production cluster. Also, we wanted to use the largest EC2 machine types as possible in order to save licensing costs, which makes quite a bit of a difference if you have a larger cluster, and it saves quite a bit of money. So that's why we're running with one Dcos cluster only. And early on, when we set up Dcos, we realized that deploying things on Dcos can get a bit complicated after some time, because we basically had to do all the automation using the Dcos CLI, and so we wrote a lot of Python and bash scripts around it, and so we ended up with quite a big mess of scripts. And we eventually built our own deployment tool called Dcos Deploy, which allows us to manage applications, services, service accounts, secrets, and so on, running on Dcos. It's also supporting dependencies between these things. So if I have an application, Marathon application that needs a service account, I can define the dependency using Dcos Deploy. And very soon, Dcos Deploy will also support deleting packages, which is still missing at this point. So maybe to give you an example, you can define your deployments using YAML files. And here on the left, we have defined an elastic principle. That's a service account, type service account. It has a name. It references a secret in the secret store, and it defines a group to which the user belongs, the technical user. And then we have elastic configuration on the right. So it's typed like Mesos framework, and where it's, and it says where it's going to be started, in which path. As you can see, we can also use variables, in this case the environment. And we have here some options referenced in JSON, how the elastic cluster should look like, and we have to define here the dependency for the elastic principle. And the only thing, after you've defined your deployment in your YAML file, you only have to run Dcos apply, and then Dcos deploy takes care of everything by itself. The cluster setup, I want to give you an example how it looks like when you set up a new cluster. So basically what you have to do is we put our installer in a Git repository, and the services definition in their own repository. So you have to check out the Terraform and the services repositories. Then you create your Terraform cluster configuration, just a regular Terraform file where you specify the number of instances and machine types. You run Terraform apply, probably have a cup of coffee because it takes some time till the instances have been spun up. And then you can adapt the regular JSON configuration files of Dcos and the Dcos YAMLs. You run Dcos apply, then the services get provisioned onto the cluster. And if you still want to restore things from a backup, you just trigger the restore scripts. And that's basically it. The cluster is ready to use. So just a couple of minutes, you can spin up a smaller cluster and then provision things, whatever you need on it. We've been running Dcos now in production for about a year, and we've made a few experiences over that time that I would like to share with you. The first thing is that the SMAC stack frameworks, they're very stable. We really didn't have any issues with the SMAC frameworks. Or in general, the supported frameworks by Mesosphere. They're very stable and mostly problem-free. We run into a few bugs, but could them either fix ourselves because everything was open source, or at least the code was available, or the Mesosphere support could help us with it. Actually, in the beginning, when we decided to use the enterprise edition of Dcos, I didn't really think we would need the support much, and we didn't get it for the support, but it turned out that it was really helpful because the people really know what they're doing, and it's quite different from how I know enterprise support from other companies. So they're actually trying to help you, and you can directly speak to engineers, so that's really helpful. And very important thing for us as well was if we fixed things, we created pull requests for Mesosphere because we didn't want to keep any forks, because keeping forks is expensive. If the frameworks get updated or if the things get updated, you have to merge the changes as well again. A second learning is that you will have to write your own frameworks and you will have to adapt existing ones. But that's okay. It's really easy to do so. It's very easy to write your own frameworks, especially with Dcos Dev that's provided by Mesosphere. So it's easy to create a new framework. You have templates, and you can get something up and running very quickly. So that's exactly what we did. So we forked the Elasticsearch framework because we needed SearchGuard as a plugin for authentication authorization, because we didn't want to use XPack, which was too expensive for us, or we didn't want to pay it. And we also updated the Zeppelin package. So the current Zeppelin package from the Dcos universe is is done by us. We created airfields, also available in the universe. And we also created etcd and console packages. The console package is already available in the universe. etcd is only available in GitHub. And we created a HiveMQ package as well, on which the upcoming official HiveMQ framework will also be based on. So the third learning was that the whole cluster installation and updates worked really, really well. We did a lot of minor upgrades. We did also a major upgrade of Dcos already, and it didn't cause a single minute of downtime. It really worked without any problems, except for Spark as usual, because some jobs wouldn't come up again. Also, node replacement worked without problems. For example, if a node was broken or we wanted to change the instance type of it, and it also supports node decommissioning. So that was really good experience, the whole Terraform installer and the Dcos upgrades. Another very positive experience was the overall stability and resilience of Dcos. So far we have been without any downtime for the last year of the whole cluster. We had some issues with the HDFS framework, but Dcos itself was very, very stable. I mean, we did multiple CoreOS updates of the nodes. We keep scaling the cluster up and down. For example, if we need GPU nodes for machine learning trainings, we kept replacing EC2 instances. And despite all of this, the cluster as a whole has been very, very stable and didn't really care about nodes being replaced. Then another, actually also very obvious learning is that that a cooperative effort with Mesosphere really helps. So we are interacting with Mesosphere a lot. We're giving back feedback. We are requesting features. We're giving back functionality that we are developing, and at the same time, they're helping us, and that's working really, really well as a partnership. So as always, treat your partners the way you would want them to treat you. So to sum it up, what's been most impressive for me is how easy it was and how little effort it took us to set up this platform. In total, the initial platform from 0 to going into production was about 5 person months, so 1 person for 5 months. And that included the migration of all data from the Hadoop cluster. And of course, it was easy for us because we kept using the same tools as before, so we only had to migrate the raw data and then recalculate everything and just set up Elasticsearch and so on in the same way as before. But still, I mean, we didn't know Dcos before, and it took very, very little time to set up the whole thing. I mean, over time we put in more effort and optimized things, introduced Dcos deploy and other things, but really to go into production, it was about 5 person months. So, thank you very much for listening. Are there any questions?
Thank you very much for your impressive speech. 자, 질문 있으신 분들 편안하게 질문해 주시면 답변을 해드리도록 하겠습니다. 궁금한 점 있으신 분들 손을 좀 들어주실까요? 네, here. 마이크를 좀 전달해 드릴까요? 네, 먼저 질문 기회 드리고 두 번째로 기회 드리도록 하겠습니다.
So first of all, thanks, Marc, to have you on stage. So, I mean, you mentioned you had on Hadoop cluster before you jump into Dcos. So, and what I have seen, so your experience was to set up the Dcos cluster very easy and quickly from scratch. So I saw within 30 minutes to get Dcos up and running. And so in case if a new customer is coming and or a new cloud provider is coming, so what does it mean in terms of setup?
I'd say if we use about the same stack, it'll take us about a week to get a system ready to run. because there you will always have to make adjustment to the cloud provider and things that are customer specific, but I don't think it will take more than a week if the technology stack is basically the same. If the technology stack running on top of Dcos is different, it will obviously take more time because you have to set up all the monitoring and alerting that is really application specific. But with the stack we have and the automation that we have and the knowledge that we have now, it should take about a week.
That's awesome. So, and can you explain us a little bit about the costs, so the operational costs between Hadoop and the Dcos framework?
Good question. Because I mentioned it, we had to put in quite a lot of effort to babysit the Hadoop cluster, and because we're working for somebody else, of course we're taking really the times that people work on certain topics. So I know pretty well how much they need for babysitting the cluster, and it's about 30% of what it was before. I mean, that's also due to the better automation that we have today. But in general, Dcos costs a lot less problems. The frameworks took care of a lot of things themselves that we didn't have to do manually anymore or automate anymore. So it's down to about a third of the time to babysit the cluster. I'd say per week, it's maybe one person day that we put into babysitting the cluster. Something like that, a bit more maybe.
That's great, thank you. So, and I mean, maybe you can give us a little bit more insights in terms why did you jump away from a traditional Hadoop cluster into Mesosphere DCS?
I think I said it in the beginning. Main problem was it didn't support all our workloads. Like on the Dcos cluster, we run databases now. We have stateless services. We have a GitLab runner. We have Prometheus and so on. All these tools weren't supported really properly by Hadoop, or in that case it was Hortonworks. And it didn't really work well. The automation, it was more difficult to automate things, and it was also causing more problems. So it wasn't a very good experience.
Okay. So, and in terms of our new release, so what are your expectations in terms of new features and what you look for?
Well, one thing that we, and I think many others, are looking for is to be even more flexible with the resources. I mean, Uber, they built their own unified scheduler for this, so they can have something like revocable resources, things like that. And that's really something that's, especially if you do the data processing with things like Spark, that's really valuable to have. And the same is true for Kubernetes on Dcos. Like right now, if you set up a cluster, the resources are still very static, and it would be nice if the cluster would see also all of the the Kubernetes cluster would see all the resources on that Mesos has, like Marathon does, basically. So you're more flexible in your resource usage in the Kubernetes cluster as well.
Okay. So, and if you have a wish list, so I mean, our president is here. So, what would be your top 3 features for the next releases?
Well, revocable resources, obviously, number 1. And then, maybe not for me, but for people setting up new clusters, even the whole setup for centralized monitoring and centralized logging, that it will be optimized. Like, for example, that you have an Elks that you can just set, provision, and then centralized logging is working. And at the moment, you still have to provision FileBeat on every node manually and things like that. But I don't want to do that. I was just install Elk package and then it's done. And I want to install Prometheus and it's done. So that's for people coming to Dcos. I mean, we have the automation for these things now, but that costs a good part of the things like that cost a good part of the effort in the beginning. don't know about the third one right now.
Okay, thank you very much.
You're welcome.
네, 탑3 피처에 대해서 말씀해 주셨네요. 자, 다음 손 드셨던 분 계시죠?
Yeah. So what's interesting from your presentation was about scaling up and down, like a Spark for machine learning, and the GPU. So we also have a little bit like a problem actually in the way we spin up like a clusters. And in our experience, when we deploy like a new clusters and we run it on like a CPU, it's not really like performing well. So we'd like to see if there's, from your experience with like a Dcos, whether there is a feature that supports like a parallel GPUs. So the GPU nodes, they are distributed across the clusters. And then like we can like program and distribute the workload across the GPU instead of just traditional nodes. Is it something that you has been supported by the platform?
Really, the only thing we had to do is to get to be able to use CoreOS for the GPU support. That didn't work right out of box because it doesn't include the drivers, the NVIDIA drivers, and so on. So. But we managed to do that, and I think there will even be a joint blog post with the Mesosphere about that, how to achieve using CoreOS instances for GPU instances. But besides that, it was quite straightforward. If you specify that you need GPU, only things that use GPU will be scheduled on a GPU node, really. And then you can also probably, if that's not enough, maybe specify using Mesos the resource roles to define what's allowed to run on those nodes. Maybe the colleagues can talk a bit more about these things, so I can ask them. But it wasn't really much of a problem after we got CoreOS to support the GPU support for CoreOS up and running.
네, 답변이 잘 되셨나요? 네, 좋습니다. 혹시 또 질문하실 분 계실까요? 네, 마이크 전달해 주시고요.
Thank you for your presenting. I have no question, but I just thank you for the EDC framework. It really saved my time and life.
You're welcome.
Because all the framework have some connection issue and clustering issue. So I make my own, but I cannot solve the EDC rejoin problem. So I just find you. I was found your team's EDC framework, so I adopted to my own framework. Thank you very much.
You're welcome. That's good to hear. It's always good to hear that the things we do is useful for other people too.
네, 감사의 메시지까지 전해 주셨습니다. 혹시 또 질문하실 분 계실까요? 네, 손 드셨고요. 마이크 전달해 주십시오.
Thank you for your speech first. I'm pretty sure once your team decided to adopt the Dcos first, then maybe your teammates would struggle to learn the new stuffs. For example, like other frameworks that you guys have to learn for Dcos, for using Dcos. Then, was there any specific issue there about learning for it?
Not really. I think what helped is that we make everyone on the team to operate and babysit the cluster, even the JavaScript developers. So kind of everybody is somehow forced to learn more about Dcos and how it works. I mean, of course, the people that are not really the experts and the infrastructure part, they will get help eventually if it gets too complicated. But in general, it was it's easy to learn, and even the JavaScript developers managed to operate the clusters.